So remember we had Noether's theorem, which basically says that the existence of a symmetry tells us that there's a conserved current. And having a conserved current means a conserved charge. Yeah. And is it an if? No, it's not. There are particularly interesting conserved charges and currents that don't come from symmetries of the theory, but come from topological aspects of the theory. So, for example, there are things called solitons that in certain theories that have an associated current, but it doesn't come from a symmetry. So it's not an if and only if. Yeah. And we looked at a very specific example. So the example was translations. Which meant that we had the following conserved current. You know, and as I stressed in the last lecture, the nice thing about Noether's theorem is that you can actually construct the current. So you really know what the current is. In this case, given a Lagrangian. Sorry, my bad. Of course, there's 4 currents because there's 4 symmetries. And these 4 objects usually, these 4 symmetries are usually put together into a tensor, which is called the stress energy tensor. And this is what we computed in the last lecture. Okay. A few comments about this, and I'm not going to write this down on the board, but it's all in the printed notes. For the specific example that we were looking at, which was just this Klein-Gordon theory, this object here, T mu nu, turned out to be symmetric in mu and nu, okay, when we actually did the calculation. That's not always going to be the case. Right? And there's no reason from this definition, although they both take the same ranges, you know, they've arisen in this calculation in rather different ways. So there's certainly no reason that once you raise this guy, the object's going to be symmetric in mu and nu. So for example, if I remember correctly, if you work out the stress energy tensor for Maxwell theory, you find out that it's not symmetric in mu and nu if you just plug it into this equation. Okay. However, having said that, in any given theory, there's always a way to kind of massage the stress energy tensor and add a few terms so that what you end up with is still conserved. It still obeys this equation with T mu nu here. But it's symmetric. Okay? So there's always sort of extra terms you can figure out to add to a given stress energy tensor to make it symmetric if it's not. And in particular, there's a very cute and simple way to derive a symmetric stress energy tensor straight off, which is something you've come across already. The theories we're considering are always just in Minkowski space. We're not considering theories in curved space-time at the moment or with gravity. But you could do the following. You could take the theory defined in Minkowski space. You could couple it to a background metric, as if you were thinking about theories in general relativity. You then differentiate the Lagrangian with respect to that background metric, and then set the metric equal to Minkowski space. If you do that, that defines a stress energy tensor, and it's exactly the stress energy tensor that appears on the right-hand side of Einstein's equations. And it's guaranteed to be symmetric. Tibra.
Could you not make the metric of Minkowski space in a general coordinate system?
Mm-hmm.
Then the metric would not be a constant quantity, and then take the derivative, and therefore that's how derive the stress energy tensor.
Yeah, I think you could probably do that. I'm going to explain a trick to compute currents for internal symmetries shortly. After I've done that, let's come back to that question. Other questions? Yeah.
If the stress energy tensor isn't or doesn't have to be symmetric, does that mean the elements have a different interpretation than they do in like general relativity?
Yeah, if you just sort of plug it into this to this equation here, for a general Lagrangian, for example, Maxwell theory, you won't get it to be symmetric. Then that's not the stress energy tensor that appears on the right-hand side of general relativity.
So what is like the physical interpretation of, because like in GR you have like this is the momentum flux and this is the...
So you still have that. You'll have the conserved quantities, which I wrote down in the previous lecture, which you integrate T00 and T0I over space. Those conserved quantities will be the same for both of these stress energy tensors. Okay, so that physical interpretation is still there, but the actual tensor itself will be gone.
Okay.
Okay, any other questions?
Wait a minute. So the stress energy tensor is, like the way you've had it at least, it's like one index up, one index down. So it's like a linear map where you put in a vector and you get out a vector, which I assume you put in a direction and you get out like the momentum flux along that direction.
If you like, but I can always raise these indices with the Minkowski metric.
So, but like when you have it like this, why would you expect it to be symmetric?
You wouldn't.
Okay.
That's the whole point.
Yeah.
There's no reason for it to be symmetric in the example we did.
Right.
Turned
And
out.
it seems like conceptually, it seems like there's no reason to want it to be symmetric.
The conceptual reason is put it on the right-hand side of Einstein's equation. There it has to be.
Oh, okay. Okay.
Okay, so there's a bunch of other symmetries that we could consider. There's ones that are rather similar to translations, and that's rotations and also Lorentz boosts. So it's an exercise. Did you all do this yesterday, or are you going to do it today? The exercise is to consider rotations and figure out what the conserved currents are, and then do the same for Lorentz boosts. You did it already? Okay, good. And for rotations, it's kind of obvious, right? It's always going to be the angular momentum stored in the field. For Lorentz boosts, it turns out to be something a bit strange. And I don't know of any situation where the need for that conserved quantity has ever come up, not in my research at least, but that could well be my ignorance. So the only time I ever saw that conserved quantity is when I've taught this course. Okay, let me give some more examples. And the examples I'm going to talk about now are called internal symmetries. Or they're sometimes called global symmetries. The word global here is to distinguish them from gauge symmetries, which we'll come across later in the course. Okay, good. So I'm just going to give a particular example. So consider a Lagrangian with a complex scalar field. And the Lagrangian is going to take the form okay, so a few things to say here. I did set you an example to sort of figure things out with a complex scalar field. So one of the points of that example was to convince you that when you're working out the Euler-Lagrange equations, you can cheat and you can think of psi and psi star as independent objects and just differentiate with respect to psi star, for example. Okay. That's really the reason that we don't have a half here when it's a complex guy. If you think back to the Klein-Gordon equation, it was a half d phi squared, and there was a half here, but there was d phi squared, so when you differentiate, the 2 comes down and cancels the half. But when it's complex, this guy is independent from this guy, so if you differentiate with respect to, say, d psi star, you just get, well, the derivative goes over, but you don't get a factor of 2. Okay? Another way of saying that is if you think of this in real fields, we can expand this guy out just with a square root of 2 there. And then this gives you the half that you need for the real Lagrange. Okay, so we're going to consider Lagrangians of this type. This potential here can be anything we like, but I'm going to insist that it's that it's going to be a function of psi star psi. Okay. Yeah.
So are you writing? You said it could be any potential we like, but you wrote down an explicit one there.
No, I'm just Taylor expanding what the possibilities are with psi.
So any analytic potential.
Yeah, I need. Let's say that for now. Yeah, and it could really be anything that you wanted at all. I haven't included terms linear in. So yeah, I'm just expanding it in psi star. In general, these potentials can be anything at all that you like. Each potential defines a different theory. However, there's very simple but actually very deep reasons why we only actually need to consider the first couple of terms in any theory, why all the other terms just don't matter in a given theory. And we'll sort of touch upon that shortly, maybe in 2 or 3 lectures' time. But there are very deep reasons for just considering, say, the simplest terms in the potential, which you will learn about as the year progresses. Yeah, please. Sorry, say again?
Do these deep reasons still work when the potential is not analytic?
Yeah, typically they'll also tell you that you don't need to consider non-analytic
Oh, okay.
terms.
Okay.
Yeah, what kind of things are you worried about? Logs can sometimes appear. They tend to be fairly important. Log of psi star psi. We're rushing ahead of ourselves by several months, so let's. Okay, for now, all I want to do is stress the following: that because of the way I've written this theory, it has a symmetry in which the phase of psi rotates. So we have a symmetry or in infinitesimal terms, okay, is everybody happy with this? Alpha here is just a constant. It's not going to depend on x. Okay, in some sense, that's what this word global means here. It's that alpha is just a constant, not a function of x. Okay, so we've got a symmetry. We can just work through that proof of Noether's theorem and figure out what the conserved current is. And we find it's the following. So again, this will give rise to a conserved charge. Notice that the current didn't care what this potential was at all. You know, all these parameters, m and lambda, they just don't arise. It's just got the kinetic terms that sit in there. Okay? It doesn't care what the potential is. Okay, so symmetries of this type are extremely important in quantum field theories. And certainly in your research, they're the ones that you're going to come across more than the other ones. You know, for the translations, you can only just do translations, and basically that's it. There's not much scope for creativity there. However, for these kind of symmetries, there's lots of interesting ways you can implement symmetries of this type. Here, it's basically just a U1 symmetry rotating a phase. In general, you could have non-abelian global symmetries where there's a whole bunch of fields which get mixed amongst each other with some non-abelian Lie group. So it's symmetries of this type, these internal symmetries, that are responsible for all the conservation laws that you've heard about in particle physics. So in particular, things like conservation of electric charge. That arises from symmetries like this. Also, conservation of particle number, conservation of baryon number, or conservation of lepton number. They also arise from symmetries of this type in quantum field theories. And we'll see exactly how that works shortly. Yeah, Darren.
I'm just wondering the exact difference between these and the symmetries we were looking at yesterday. Yesterday we were doing active transformations on the field. these are the difference. These
These aren't affecting space. That's really the key difference. This is why what the word internal here means. Sorry, I should have stressed this. The other symmetries, the rotations and the translations, they were doing something to the underlying space and seeing how the field reacts. Or in an active sense, it's not quite that. But it was all to do with the symmetries of space, time, and then seeing how that affects the fields. Here, we're not doing anything to space. We're just changing the value of the field at a given point in space. So that's what this word internal means.
So that is, we're not changing the arguments, the coordinates.
Yeah,
to
exactly.
solve.
Please.
Is this current the same, more or less, current as you get when you look at local U1 gauge symmetry?
Yeah, we'll come to that, but you're right. I should have stressed this. It's the kind of current that you get in electromagnetism. Okay. But the field theory version of those currents. And we will get to a point where we gauge this, and this really becomes the U1 of electromagnetism. But that's going to be in the third week of this course. Okay. By the way, just in case there's some confusion, I told you just now that symmetries of this type give rise to conservation of particle number, like baryons. But I told you right in the first lecture that the whole point of quantum field theory was that you don't have fixed particle number. So what's going on there? Well, conservation of particle number means you count particles and antiparticles with pluses and minuses. Okay, so it doesn't mean the number of particles is fixed. It means that the number of baryons minus the number of antibaryons is fixed. So that's always what people mean when they refer to conservation of particle number in quantum field theory. Okay, are there any questions about this? I'm just going to tell you a cute trick because I'm just repeating myself, but the stress energy tensor is something that there's one stress energy tensor for every theory, and it's very easy to calculate it. However, there can be lots of interesting internal symmetries in different theories, and certainly as you do research, you'll come across a new Lagrangian, and you'll have to figure out what the current is associated to it. You won't be able to look it up in Peskin and Schroeder. So it's worth just knowing a very cute trick to calculate these currents for internal symmetries. So let me just tell you this. Okay. So cute trick. So suppose we have an internal symmetry such that delta L is equal to 0. Okay. And there's going to be some parameter, or maybe a bunch of parameters, alpha, which are the constants which tell us sort of how much we're implementing this symmetry. Just like here, they tell us how much we're rotating the phase of psi. So the trick is the following. We'll redo the transformation with alpha not now constant, but being a function of x. Okay? So just to stress, we're not promoting this symmetry to a gauge symmetry. For those of you who know about gauge symmetries, there's no gauge field floating around. We're just redoing the symmetry transformation, but with these parameters alpha now varying on x. Okay? What's going to happen? Well, this is no longer going to be a symmetry. And in general, delta L is going to change. But it's got to change in a way such that when alpha is constant, delta L is equal to 0. How can that be? Well, delta L must be proportional to the derivative of alpha. Okay, is that clear? This is the only kind of transformation you could have so that when alpha is constant, delta L is is vanishing, as it must for a symmetry. There were a couple of questions. Yeah.
So how would you generalize this? It clearly doesn't work if you have an overall derivative that's your change in the Lagrangian, right? Which is also a symmetry. How would you generalize this?
That's a good question. So those derivatives, let me come back to that question after I've done this, because I did want to make a comment about it. Yeah. Was there another?
Yeah, I had this. Well, I guess I didn't understand what it meant. We do the transformation of alpha x.
Okay, so let's consider this particular transformation. We vary the phase of alpha, but we have to do it the same everywhere in space.
Yeah.
So I'm saying now take your Lagrangian and do a new transformation where this differs in space. That's not going to be a symmetry of your theory, which means your Lagrangian is going to change, but the way it changes has to be of this form.
Wait, so we can't do this with a general symmetry? This is specifically for that kind of...
It's for any, at the moment, it's for any internal symmetry. So there's a bunch of alphas which are parameterizing how much of the symmetry you're doing, how big your rotation is, how much you're mixing up different fields.
So, I guess I missed something. No, I think I missed something at some point, so I'm confused.
Okay. You want me just to say it all again, or
No, I'll try to figure out what's going on and then I'll ask you later.
okay?
Does the differential operator there apply to h? You said it just has to be proportional to, right? Okay.
Okay, so there's some function h in the field such that the variation of the Lagrangian is the derivative of alpha multiplied by h. Okay. This means that the change in the action is obviously the integral of the change in the Lagrangian, which after an integration by parts takes the following form. Yeah, good.
So you say an internal symmetry is one that involves a transformation of fields and acts the same at every point in space-time.
Yeah.
So I see. Why do you say all internal symmetries help alphas? What does that mean?
So the internal symmetries are always continuous symmetries.
Okay.
Right? They're never just parity, reflection.
Right.
It's always something continuous. That means that there's got to be some parameter that tells you how much of the action of the symmetry you're doing. I'm just calling that parameter alpha.
Okay. All right. So my second question then was: is it supposed to be obvious that that you have to have it has to be proportional to the derivative?
It's got to be proportional to the derivative because as soon as this alpha is constant, delta L vanishes because it was a symmetry to begin with.
And you can't imagine it L vanishing even though alpha is not constant because.
You could, but that's certainly allowed. H would be 0 in that case. Right? There's some function h such that.
I'll get back to you.
Okay, so now comes the clever trick. The clever trick is that when the equations of motion are obeyed, which we haven't used so far, delta S is always 0 for any transformation that you want to do. Whether alpha depends on x or not, whether it's related to the symmetry or not, the whole point of the equations of motion is that delta S vanishes however you change the fields. Okay. The equations of motion imply that delta S is 0 for all alpha of x. And the only way this can happen is if the derivative of h vanishes. Okay? So h is the conserved current in this case. So this is the Q trick. You have some theory. It's got some internal global symmetry that you want to figure out the current for. What you do is you pretend that global symmetry changes in space, so you promote alpha to a function of x. And then you just work out how the Lagrangian changes. You'll see that it's always proportional to the derivative of alpha, and there's an h there, and you just read off that h. Okay, it saves you a lot of work. So since I see some blank faces, let me just set a couple of exercises. So the first one is use this trick for the previous Lagrangian. Okay, so this should give you some sense for how this trick works. It's fairly straightforward, especially as you've got the current, so you know what you're aiming for. The second exercise is very difficult. And I'll be impressed if you can do this. And it comes back to your question. Use this trick to show that the stress-energy tensor, which remember we've defined as the conserved current that comes from translations, is the same as that arising in general relativity. By which I mean theta mu nu equals 1 over the square root of g ds by dg mu nu. Okay. Yeah, this is pretty tricky, and you have to deal with this issue about the fact that there's an extra total derivative when you vary when the delta L is not 0 but is a total derivative. Right, so you've got to find a way around it. And actually, it's not quite T mu nu because this is always symmetric and this isn't. So there's various subtleties.
What is that you wrote down?
Sorry, so this is the differentiation of the action with respect to the metric g mu nu. So this is the definition of the stress-energy tensor in general relativity, and then there's 1 over the square root of g. And there's probably minus signs. This is the determinant of the metric, right?
Yeah.
Okay. I'll walk you through this maybe this afternoon, or oh no, you're not doing anything this afternoon, right? So maybe tomorrow afternoon. If people are interested, I'll walk you through this. It's a nice argument, but it's a bit subtle. Okay, that's it for Noether's theorem. Are there any questions? No? There's one more small thing I want to do about classical field theory, and then we're going to turn H-bar on. Okay, so the last thing I want to do is the Hamiltonian formalism. Okay, so far we've been working with the Lagrangian formalism, but you all know how to go from Lagrangians to Hamiltonians, and it's exactly the same in field theory as it is in particle mechanics. So first thing we do is we define the conjugate momenta. Okay, the major difference between field theory and particle mechanics is that we call this pi instead of p. Okay, that's really it. The reason for this is that we've already got something called p. Remember, we figured out the conserved quantity associated to spatial translations, and we call that p. That's not to be confused with this. Okay, that p is a number, and it tells you how much the field is going this way. This conjugate momentum is obviously a function over x and is not the same as that p. Okay. Okay, the Hamiltonian density is then defined in the usual way. I'll denote it by a curly h. So it's the momentum times phi dot minus the Lagrangian. And just as in classical mechanics, you should view this not as a function of phi dot, but everywhere there's a phi dot, you should view that as a function of pi defined by this equation here. Okay, so you should view this as a function of the conjugate momentum pi and the fields phi, but not phi dot. Exactly the same story as usual. Yeah.
When we defined the Lagrangian for fields, we said that we also needed spatial derivatives. Why don't we need spatial derivatives here for the conjugate?
Because the Hamiltonian formulation of field theory is not manifestly Lorentz-invariant. It picks out a time.
Okay.
And so what we're left with here is not something on which time and space are on equal footing. Time is special in the Hamiltonian formulation.
Is that why you said that Lagrangians are preferable?
That's why Lagrangians are much better, because you look at a Lagrangian, you know immediately that it's Lorentz invariant or not. You look at a Hamiltonian, it could take some work to figure out whether or not it's Lorentz invariant. Of course, it is Lorentz invariant. The physics is Lorentz invariant because nothing's changed, but it's not manifestly Lorentz invariant. The equations don't look. So let me just say viewed as a function of time. Yeah, please.
Lagrange is dependent on phi or on x.
Probably a better way of saying it. And it depends on phi, phi dot, and grad phi, but they're of course all functions of x. Okay, so let's just look at an example. And of course, it's going to be the example that we've been considering all along, just a real scalar field, Klein-Gordon theory. Instead of writing the, well, actually, let me take a real scalar field with a general potential, V of phi here. Usually I'd write this as d mu phi, but I've separated it out just because obviously we're going to differentiate with respect to phi dot. So in this case, it's very clear that the momentum conjugate to phi is just phi dot, which means that the Hamiltonian density, I should say, so the Hamiltonian is given by the following function, and the Hamiltonian density is given by the following function, and the Hamiltonian you get by integrating the density over 3 space, just like for Lagrangians and Lagrangian densities. Okay, questions? No, it's all straightforward. It's all exactly the same as in particle mechanics. Again, just to stress, the Hamiltonian formulation of field theory picks out a time, okay? Right from the very beginning. Defining the conjugate momentum picks out a time. So this is not a Lorentz invariant choice. Obviously. Yeah.
The h, which is the integral of the Hamiltonian density,
Yeah.
how does that compare with the zeroth component of the charge, which is conserved?
Good. So it's just like in particle mechanics. If you take simple systems, you compute the Hamiltonian, that's very often equal to the energy that you compute by time translation invariance in the Lagrangian. And you can see that we computed the energy for this, and it's exactly the same for this simpler theory. Now, just as in particle mechanics, it's not always true, right? I mean, there's subtleties, especially if you've got gauge connections and various things. So in this case, this is equal to the energy E that's the conserved one. Okay, other questions? No? All happy? Good. Good, so that's the end of classical field theory. So now we're going to turn to quantum field theory. From now on, h bar is equal to 1 instead of 0. Okay, so this is section 2. And it's canonical quantization. And I guess the one thing I really want to stress in this section is that there ain't nothing special about quantum field theory. What we're going to do is take the procedure that we've learned in quantum mechanics and just apply it to this classical system. Okay, there's nothing mysterious about what's going on here. It's really just a straightforward run-through of what you've done time and time again in quantum mechanics. So we're just going to do this. So recall, in quantum mechanics, canonical quantization tells us to take coordinates and momenta so the coordinates I'll call Q and the momenta I'll call P, and promote them to operators. Then what happens? Well, if you know a bit about the Hamiltonian formulation of classical mechanics, what you really do is you take the Poisson bracket structure or the symplectic structure on phase space, and you change those Poisson brackets to commutators. Okay, all those fancy words really mean is that for most systems, these Q's and P's are operators which obey the commutation relation. QP is I, and typically there's an h bar there, but of course h bar is 1. Okay.
This is a really minor point, but how do you know to put the index on Q downstairs and the index on P upstairs?
Well, it comes from the definition of P. One's up, the other's down.
Okay. So that's then the P that we have over that you said.
No. So this is just reminding you about what happens in quantum mechanics, and now we're just going to take this and translate it to this pi and this pi. Okay, exactly the same. Other questions? Okay, so in field theory, we're going to do the same for phi of x and pi of x. Okay, so a quantum field is an operator valued function over space. Okay, and I really mean space here, I don't mean space time. I'll clarify this point shortly. Okay, obeying the commutation relations well, it's really just these commutation relations, but applied to phi and pi. There's the trivial ones that I didn't write down here. QQ is 0 and PP is 0. So let me just write these down here. So again, let me come back to a point that I've been stressing over the last few lectures. In quantum field theory, the x, which is the spatial position at which the field is just another label. It's a continuous label instead of a discrete label, but it's just another label. It's basically on the same footing as the A index here. Okay? So just as here, it's clear that I should write A and B just being different, that any coordinates commute with each other. So I should write x and y being any coordinates. They should be different, x and y. Okay? Just another label. That also tells us what the correct interesting commutation relation is between the coordinates and the momenta. So there's an I, and we know we need a Kronecker delta for any discrete indices that are floating around, because that's the same as in quantum mechanics. But now we have one other label, which is x and y, and they should also just have something like a Kronecker delta. But it's a continuum, so it's not a Kronecker delta, it's a Dirac delta. Okay, the question.
So you said that the x's and y's are just labels, but are they still operators?
No, they're definitely not operators at all here. In quantum mechanics, the dynamical degree of freedom is the position of a particle, and you promote that to an operator. In quantum field theory, position is not an operator at all. It's just a label. So the phi's are operators, and this is just an operator. Okay? It's worth saying this over and over again, because it's the big difference between quantum mechanics and quantum field. You know, when you first do quantum mechanics, x is an operator, and time is just a label. And so you get these nice, uncertainty relations. Delta x, delta p equals, is greater than h bar. And you think you hopefully get uncertainty relations like delta e, delta t is greater than h bar, but t isn't really an operator, and you're not sure how to interpret that. You remember these sorts of... And so, in the back of your mind, you're probably thinking, wow, what I really want to do to get x and t on the same footing is take t and turn that into an operator as well. No. What you want to do is take x and demote it to the same framework as t. It's just a label. Okay? So that's what quantum field is. X and t on the same footing, but both like t in quantum mechanics, not both like t. Yeah.
I want just to know whether x and y were 4 vectors or 3 vectors.
They're 3 vectors. They're functions over space only and not space-time. And the reason is, now's a good time to say this. We're in the Schrödinger picture. Okay? So again, just like in quantum mechanics, in quantum mechanics, in the Schrödinger picture, the operators don't depend on time, and all time dependence sits in the state. Okay? We're doing exactly that. The operators don't depend on time, but they do depend on x. Of course, time and space are on different footings now, but that was necessary as soon as we defined momentum. As soon as we defined these guys here, we'd already picked out it. So we've broken Lorentz invariance in our mathematical formalism, but the physics should still be Lorentz invariant because it came from a Lorentz invariant.
Will we ever recover?
We'll work very hard to show exactly how Lorentz invariance is recovered and in what way it's recovered. Once we go to the Heisenberg picture, it becomes a bit more apparent. Yeah.
Phi index A. Phi A and Phi B are in general different fields.
Yeah, I've got 1,752 fields, and they're labeled by A goes from 1 to 750.
Do they always commute?
Yeah. Just like coordinates in they always commute, apart from when they don't. It's the same question whenever you ask something difficult, I'll say yes, apart from when they. And they anti-commute as well is the other familiar thing. But we'll get to this. Were there other questions? Let me just write down this issue about the Schrödinger picture because it's important. So we are working in the Schrödinger picture. where phi of x depends on space but does not depend on time. Okay, so where's the time dependence? All the time dependence sits in the state and how the state evolves. And how does it evolve? Well, it just evolves by the Schrödinger equation. It's exactly the same as in quantum mechanics. So what's the Schrödinger equation? Well, it's exactly the same as you've seen 100 times. Yeah, this equation looks deceptively simple, but this state is horrendous. So again, think back to quantum mechanics, because it's exactly the same as quantum mechanics. In quantum mechanics, you have a particle, and its degree of freedom is that it can live anywhere in R3. This state, in that case, is a wave function over R3. So it's some function over the configuration space of the particle, which is R3. Okay, that's the usual quantum mechanics hydrogen atom kind of thing. So what about field theory? The configuration space of the field theory is any possible configuration the field can take. So this wave function is a function over the space of all possible field configurations. So it should probably be called a wave functional. It's a function of a function. Okay, so this, if you were to write this down in some Schrödinger picture, it will tell you the probability for the field configuration to be like this, and the probability for the field configuration to be like this, and for every field configuration, this would spit out a complex number. Yeah, it's very rare in quantum field theory that we actually use that language just because it's horrible. Okay. Occasionally you do, but it's rare. Yeah.
So this is some detail, but do wave functions in quantum field theory, are they smooth functions on the space of fields, or are they linear functions?
Since I've never written one down, I have no idea. I'm not smooth or linear, but those two are.
I mean, because the space of fields is like a manifold, but it's also a vector space. So like, you could imagine it would be nice and it would be linear functions on the space of fields.
Linear function. That means no. I don't see why it would be linear. I mean, R3 for a particle is also a vector
Right,
space,
true.
but the wave function certainly doesn't have that property.
True, although waves, like, you know, fields typically have the nice properties of, like, you know, superposition, like, that sort of thing, like the electromagnetic fields.
Same is true for, yeah, I think the answer is no. The linearity of the field theory is not.
Yeah.
We'll see. We're not really going to use this wave functional language very much because it's horrible. Well, we will start to write down sort of some representations of this wave functions.
The Schrödinger equation, is that an extra assumption on quantum field theory? That's the first question. The second question is that the Hamiltonian, if you look at the Hamiltonian that you derive, say, for the scalar field, that's quadratic, whereas this is, again, we have the problem of not being Lorentz invariant because it's first.
You're right. Nothing looks Lorentz invariant, but everything is. And we will work to restore the Lorentz invariance manifestly in the equations. But you're right. Time appears here and nowhere else, and space appears in the operators, and it all looks awful. The first question is this an assumption? There are no new assumptions in quantum field theory. All we're doing is taking quantum mechanics and applying it to a different classical system with an infinite number of degrees of freedom. Okay, so it's as much an assumption as in classical as it is in quantum mechanics. Commodore Garden quantum mechanics. Other questions? Okay, so what do we want to do? We've written down this Hamiltonian in terms of our fields. And the fields have now been promoted to operators. But by the way, I'm not going to do this thing where I write hats on operators. You know, that's so undergraduate. So we're just going to have to remember that phi and pi is an operator once we're talking about quantum mechanics. Okay, so we've got h, which is now some function of operators.
So you're saying, like, you point out those things, you say fields have been promoted to operators, but this seems equivalent to me to, like, pointing at the position and momentum operators in, wave mechanics and saying particles have been promoted to operators. Like,
Not particles, but degrees of freedom of particles.
Right.
Yeah.
So I'm wondering it's the same here, right?
Exactly
it's degrees
the
of
same.
freedom that are promoted to operators.
Yeah, this was the classical degree of
Right.
freedom, and this was its conjugate
Right.
momentum. This was Q, and this was P. And you know, when you're undergraduates, you put hats on them, and here we just say they're operators. Okay, so we've got this Hamiltonian. It's now an operator.
Sorry. Operators on what exactly? And what do they extract when they operate on it? Or what?
Good. So operators on a Hilbert space that we've introduced, which the one small definition I've given you so far is that it's the space of all functions on all possible field configurations. So it sounds horrid. We're going to
Solidify that.
yeah we're going to see concrete examples of what these Hilbert spaces are. They're a little bit more infinite dimensional than the usual Hilbert spaces you consider, but nothing horrible.
They're not.
Okay, we've got a Hamiltonian, and no questions. We've got a Hamiltonian, and it's a function of certain operators, and the thing we would love to understand is the spectrum of this Hamiltonian. Okay, that's the simplest thing we could hope for. What are the eigenvalues of this Hamiltonian? As you could imagine, that's an extremely hard question. Okay? Well, we can solve it for the harmonic oscillator, and we can solve it for the hydrogen atom, but we can't solve it for the helium atom because it's got 6 degrees of freedom, I guess. Okay? Here we've got an infinite number of degrees of freedom, and it's going to be very, very difficult to figure out what the eigenvalues of H are for a quantum field. Okay? And indeed, you know, you may have heard about lattice QCD programs where people spend 5 years building computers that are about the size of this room, and the computers run for 5 years, and they get the spectrum of the Hamiltonian of QCD to maybe 5% accuracy. Okay? It's an unbelievably difficult numerical problem for certain field theories. Thankfully, there's one class of field theories where we can do this. And they're what's called free field theories. And the beauty of these free field theories is that although there's an infinite number of degrees of freedom, if you write them out in good coordinates, they all decouple from each other, and you find out that each of these degrees of freedom is just evolving independently of what all the other ones are doing. Okay? So it's with these free field theories that we're going to work for the next couple of lectures, and just understand in them what the spectrum of the Hamiltonian is, and what the interpretation in terms of particles is. Okay? Okay. So we want to know the spectrum of H. This is hard, okay? Where this sentence is a dramatic understatement. Okay? You know, for QCD, it's also in some sense one of the Millennium Prize problems in mathematics to understand this spectrum. Okay, it's hard because there's an infinite number of degrees of freedom. at least one for every point in space. Okay, so we can make progress in free field theories. Okay, so if you want a quick and ready definition of a free field theory, it's a theory where if you look in the Lagrangian, the fields only appear quadratically. What that means is that if you look in the equation of motion, the fields only appear linearly. And as you all know, that means that if you've got one solution, you can add it to a second solution and get a third solution. So these have Lagrangians which are quadratic in fields, which implies the equations of motion linear. Okay, and the simplest free field theory is the one that we've been mentioning in all the examples. It's just the Klein-Gordon theory. Okay, so this is the Klein-Gordon theory. So let's just figure out how to solve this, and just this classical equation. And if seeing how to solve it, we'll see why it's free and why all these degrees of freedom are really evolving independently. Okay, so to solve it, it's very easy. All we do is we do a Fourier transform. Okay, so I just rewrite phi of x in terms of the Fourier transformed field, phi of p. I'm going to call them both phi. Hopefully that won't cause too much confusion. By the way, my conventions for Fourier transforms are always going to be that whenever there's a p integral, there's a 1 over 2 pi that sits at the bottom. Okay, you know you can sometimes split the square root of 2 pi's between x and p, but this way is much easier because you know where the 2 pi's should be. They should be where the dp's are. Okay. You guys all happy with Fourier transforms? Is that?
Yes. Just what's p? P is the momento. Is it the conserved momento of the field?
It's we're doing a Fourier transform with respect to x. So you could think of p just as what you need to do the Fourier transform with respect to x. It's not pi. Okay, it's not the conjugate momentum of phi. Right? So it's a 3 vector. It's also not the conserved momentum associated to a field. Given if we have a field configuration phi of x, we can just rewrite it in terms of a new one phi of p, and they're related in this way.
So this is defining 5p.
Sorry?
Is this defining 5p?
Yeah, if you like, yeah. Well, yes. Yeah. But you see, it's a dummy variable. I could have called it p, I could have called it q, I could have called it anything. Just integrated it.
So it's just some decomposition of the field.
That's the best way to think about it. Of course, what it's really going to do, you have phi of x, and it's really doing what Fourier transform always does. It's telling you, given this, how much, and you decompose it into something that wobbles this quickly and something that wobbles less slowly. So it's the usual p in that sense that appears in all Fourier transforms.
Thank you.
So it's basically a relabeling of x in a way that gives you that information.
Not a relabeling, but a reshuffling of how this,
Right,
this function
that's one.
depicted. Yeah.
Yeah, okay.
Is there another question?
No,
I was just wondering where the T came from.
Where?
The phi is supposed to be, there's not supposed to be a T in.
Oh, good. You're right. I'm backing up. I'm thinking of this as a classical field equation. And as a classical field equation, phi is something we need to solve for. It depends on x and t. Shortly, we'll then run through this analysis, and then we'll see what that means for the operators. Yeah, good.
and I guess a quick question. Just like this Fourier transform of the field operator, like, so this is an integral of an operator.
Not at the moment. It will be shortly. Classical Klein-Gordon equation.
Oh, okay.
We're just going to.
Okay.
So it's nothing fancy. Yeah. Sorry, I should have stressed this. Let me. So there's a classical equation. Okay, so we take this, we plug it into the Klein-Gordon equation. And what we get is an equation for phi of p that doesn't depend on any of the other phi of p's. So each of these phi of p's just evolves completely independently and has to obey this equation here. But this equation here is just the equation for a harmonic oscillator. Okay. The frequency of the harmonic oscillator is this guy here. This is going to be something that arises over and over again in the next couple of lectures. So we're going to give it a name. We're going to call it omega subscript p. Okay. Okay, so what's the solution to the classical Klein-Gordon equation? Well, it's a superposition of harmonic oscillators, an infinite number of them, labeled by this 3-vector p. Each of these guys is oscillating in time at this frequency, so they're each oscillating at a slightly different frequency. And then to find the most general solution to phi of x, you just add them all together with arbitrary amplitudes, whatever amplitude you like, and integrate to do the inverse Fourier transform. Okay?
Why did we do not consider the negative?
This is my definition of omega p. What sits in here is omega p squared. So I'm just defining omega p to be the positive square root. It'll be useful. Okay. Okay, so let me just one second. Let me just stress what we've done here. We're just thinking about the classical field equation, and it's really just a statement that because it's linear, we take one solution and we add another solution, we get a third solution. So what I'm doing is showing you explicitly what the decomposition is. the degrees of freedom which vary independently and don't couple to anything else, they're the Fourier modes phi of p. So each of these modes is oscillating some frequency given by this. You add them all together, and you get the general solution phi of x. So this is what I meant earlier, that from the infinite number of degrees of freedom, if we figure out what the right coordinates are, we see that they actually evolve independently. These are the right coordinates. Bunch of questions.
It's a spatial frequency then, since there's no...
No, it's the temporal frequency. It's the frequency of the harmonic
But
oscillator.
our Fourier integral was with respect...
It's just space. Right, but each of these phi of p solves this equation.
This is related. Intuitively, it's entirely obvious. Like, this is a wave equation, and the solutions are plane waves.
Yeah, it's just that.
So
Yeah, it's just
each of these things has a space frequency and a time frequency, and those two things are related. Yes.
Yeah. Tibor, you had a
This is the analogy with the harmonic oscillator is that with the Schrodinger equation of harmonic oscillator, although we are treating it as classical systems, but that equation is what we would get if we consider the Schrodinger equation. Right? So it's
x double dot plus omega squared x equals 0. Right? It's high school harmonic oscillator, classical harmonic.
But,
no,
I mean,
it's a Schrodinger equation. I mean, phi is the wave function.
No, phi is certainly not the wave function. It's a classical field. Nothing to do with the wave function at all. Nothing.
Oh,
at all.
I see. Okay.
Yeah, it's a classical field, and we're just solving this.
Yeah, so just to be clear, so if you were in high school, you would not call this harmonic oscillator. You would call it a plane wave with
I'd call this the harmonic oscillator
with
equation
number
labeled.
K and
It's only because the p is here and not here that you're worried, right?
no,
It's an infinite number of harmonic oscillators. This is a label that tells you which
no.
particular
Like
degree
each
of freedom.
solution to this equation is a plane wave with wave number K and frequency, angular frequency omega. And yeah,
It's not difficult, I think, is what we're all saying. It's just. Okay, so what we've got is a bunch of these degrees of freedom. Each of them obeys the harmonic oscillator equation. And now we're going to quantize. So now we're going to turn this into an operator, but all we then have is a bunch of infinite simple harmonic oscillators, which we're quantizing. Okay. So so solutions to the classical Klein-Gordon equation are superpositions of simple harmonic oscillators. So to quantize phi of x, we need to quantize harmonic oscillators. But we can all do that, right? That's fairly straightforward. So what I'm going to do in the last 5 minutes is something very boring. I'm going to fly through at great speed a review of the quantization of the harmonic oscillator, which I know you've seen 1,000 times, but at the very least it will just get notation on the board, and then we can move on.
so I feel like there's been some sort of sleight of hand. Like, we had a bunch of plane waves, and now we say to treat the plane waves quantum mechanically, we say they're simple harmonic oscillators. What's, like, I mean, I understand they're related somehow, but like...
Let me move on, and then
Yeah.
we can discuss this later, because time is short. And I'm not sure how to answer the question, because I don't think it has been Okay, so this is going to be very straightforward. You know, Michael Peskin likes to say that physics is that subset of human experience which can be reduced to the simple harmonic oscillator. It's completely true. It's basically the only thing we can solve. So in the Schrodinger picture, This is the harmonic oscillator, Hamiltonian, and Q and P are operators now which have familiar commutation relations. And to find the spectrum, what we do is we define these nice creation and annihilation operators. Okay, nice and familiar. If we substitute these, if we work out the commutation relations, substitute in these expressions, use the fact that P's commute with P's and Q's commute with Q's, and P and Q commute to give I, we find that these have the following commutation relations. And we can also write H in terms of A's and A daggers. We get the following form, or we could choose to commute the A and the A dagger past each other so that they're both ordered in this way. In which case the Hamiltonian takes the following form. And finally, the important fact about these creation and annihilation operators is that they have these commutation relations with H. So what this means is that if we've got one eigenstate of H, we can act with A and A dagger and get another eigenstate of H, another energy eigenstate. Okay, so we get this tower of energy eigenstates. If there's one with E, there's another one with energy E plus omega, and another one with energy E plus 2 omega, and so on and so on. And there's one with energy E minus omega, and one with energy E minus 2 omega, and so on and so on. But at some point, if we want to have a spectrum which is bounded below, this had better stop. And this stops only if A acting on one state vanishes, so that we don't have another state to go to. So spectrum bounded below implies that there exists a ground state, which is defined by the fact that it's annihilated by the annihilation operator. So I just rubbed off this equation we had for the Hamiltonian, but when we act with the Hamiltonian on the ground state, this term kills it, but we're left with this guy here. Okay, so this should be very familiar. This is the ground state energy, the 0-point energy of the harmonic oscillator, a half h bar omega, but h bar is 1. Okay. I know all this is boring and familiar, but we're going to see exactly the same thing for the field tomorrow, so it's worth going through. Then excited states is where you put exciter state for each integer n, where you hit the ground state with n creation operators. That's not normalized, by the way. There should be a 1 over square root of, I don't know, n plus 1 or something like this. Okay, so this is the spectrum of the harmonic oscillator. Ground state energy of a half h bar omega, and then a tower of states equally separated above, whose energy increases by omega each time. Okay, is there anybody that's not familiar with this? Good. So now what we're going to do in the next lecture is have an infinite number of these, all shaking at once, and we'll see what we get out of that and how we can interpret that in terms of particles moving in Minkowski space. Okay, good. See you tomorrow.